Why, hello! It is Miss Heaton signing in to talk with you about another method for using ice charts and KEQ equations to solve for equilibrium concentrations. This is when you're trying to find the value of x, and this method is best when you have a very, very small KEQ, because what that means is that your reaction, if your KEQ is small, remember KEQ is products over reactants. So if this is a small number, that means you have a lot of reactants. You have a big number on bottom and a very small number on top, which means your reactants are highly favored, which means that your reaction is not going to proceed very much. If you're starting with only reactants, the x value is going to end up being small, so your change value is small. How can you tell if you can use this method? That's probably what you care about most. Here's how. If you compare your initial reactant amount to the concentration to the value of KEQ, and the concentration divided by the KEQ value is bigger than 1,000. So if the concentration is at least 1,000 times bigger than the KEQ value, then you can use this method. So basically, you would set up your ice chart and your KEQ, and then try to figure out whether your concentration of your initial stuff is big enough to approximate. So we're going to try this example that you see here. NaCl2. So let's go ahead and write out our ice chart. 2NaCl is an equilibrium with 2 NOs and a Cl2. So I, C, and E. Initially, we put 2 moles in a 2-liter flask of our reactant, so that would be 1 molarity to start off with, and neither of our products. Our change here would be minus 2x, plus 2x, and plus x. And at equilibrium would be 1 minus 2x, 2x, and x. Our KEQ equation will be K equals products over reactants. So it'd be 2x, remember it's squared because there's a coefficient of 2. People always forget that, and I'm not entirely sure why. It is kind of tricky, but you got to make sure you do it. And then 1 minus 2x squared on bottom. And we know that the KEQ value for this equation is 1.6 times 10 to the negative 6th. So it's a pretty small K value, and we did start with a relatively large amount of our reactant. So let's see if we can approximate. So again, this is how we can tell if we can approximate. So I'll do that work up here. Our initial concentration of stuff was 1 molar. So if we can approx, we would do the initial concentration of our reactant, which is 1, divided by the KEQ value, 1.6 times 10 to the negative 6th. That turns out to be the lovely and large value of 625,000, and that is bigger than 1,000, so yes, we can approximate. If you couldn't approximate, what would you do? Well, you'd have to use one of your last resort strategies, either the graphing method or the quadratic method. What this means is that x is really small. Since the reactants are so highly favored, you're not really going to be losing much of your NaCl because x is a really, really small number. And so what we can do is anywhere that x is being added or subtracted or added, not multiplied, we can assume that it's 0. And here's why. Because even if x was a small number, it would matter in our numerator. We can't just assume that the numerator is 0, because a little bit of NO and Cl2 are made. But our ending amount of NaCl, our reactant, is going to be pretty close to where it started. So we can assume that this change is virtually 0. So what that turns our KEQ equation into is 2x, the quantity squared, times x, over 1 minus 0 squared, which is just 1. So then we have 1.6 times 10 to the negative 6th equals 4, oops, I didn't mean to put that squared in here, 4x squared times x, so that's 4x to the 3rd. Then divide both sides by 4. So x to the 3rd equals 4.0 times 10 to the negative 7th. Then to get x by itself, we could cube root both sides. So make it to the 1/3 power. So then X turns out to be 0.0074. And we can then take that number for X and plug it back into our ice chart, into our equilibrium row. So 1 minus 2X, 1 minus 2 times 0.0074. By the way, X is a really small number, so this makes sense. When you plug that in, you get about 0.99 molarity. Whoa, that's basically 1, so our approximation was probably good. And then 2 times X will be 0.015 molarity for our NO. And for the Cl2, it'll be 0.0074 molarity. And that's how you approximate. This is probably my favorite method. I would love to hear about yours, so please tell me when you see me in class. This is Miss Heaton, signing out.